After a detailed description and discussion of basic fundamentals of classical statistics, now we will start to deal with the proper theory of classical statistics. As you know, the classical statistical mechanics is also known as Maxwell-Boltzmann statistical mechanics because the classical statistics is based on the Maxwell-Boltzmann distribution law. So it is essential for us to know that in which condition we will be able to apply the concept of classical statistical mechanics and for what system we can apply this classical statistics. So selection of system for which classical statistical mechanics concept can be applied or the Maxwell-Boltzmann distribution law can be applied, it is very essential to know. Okay? As you know, in the basic lecture, I have discussed already that in classical statistics, whenever we consider a system of particles, the particles of the system must be identical but distinguishable. This is the basic criteria. Classical statistics will be valid only for that system whose particles are although identical but that can be distinguished. Okay? But how we can say that particles are distinguishable? In fact, this criteria of distinguishability of particle can be thought only in terms of the quantum mechanics. Because you know, in quantum mechanics, we always talk about the wave associated with a particle. Whenever you talk in terms of quantum mechanics, you say that if there is a particle, let us say this is a particle, this particle is definitely confined within the wave packet associated with the particle. So if this is the wave packet associated with a particle, definitely this particle is found somewhere inside its wave packet. Okay? And let us consider this is another particle and this is the wave packet of the another particle. Okay? If the wave packets of these two particles will overlap, will superpose, actually in that condition the particles cannot be uncorrelated, they will be correlated. So the two particles will be not correlated, it means the two particles are distinguishable only when you can say that the wave packets of the two particles do not overlap with one another. Okay? So for distinguishability of particle, it is a must condition that the wave packet associated with particles do not overlap, they do not superpose. Okay? But how we can say that the wave packets associated with particles do not overlap? Actually, this will be only possible when the extension of the wave packet of the particles will be much smaller than the interatomic separation of the particle, or you can say interparticle separation. Say this is particle number 1 and this is particle number 2 and this R is actually the interparticle separation. So if you can say the wave packet or the de Broglie wavelength associated with the particle is much smaller than this interatomic separation, only then the particle will have individual identity. They will be not correlated, and that can be treated like distinguishable particles. Okay. So this is the basic criteria that the particles can be distinguishable only when the wave packet, which is actually some multiple of wavelength, that is de Broglie wavelength associated with the particle, the extension of that wave packet is much smaller than the interparticle or intermolecular separation between the molecules or particles. Actually, this condition can be fulfilled in case of a perfect gas, but perfect gas, or you can say a dilute gas, because perfect gas is just an ideal situation. It does not exist in practice. So in practice we always take a dilute gas, that is a gas of very low density. So if a dilute gas of low density is at very high temperature, then actually the intermolecular separation or interparticle separation is large, and in that very condition it is possible that the de Broglie wavelength associated with the particle can be much smaller than the interparticle separation, and then the molecules of such a dilute gas will be not correlated to one another, that those can be treated actually distinguishable. Okay. So in fact, while dealing with the classical statistical mechanics, we can take as a system the dilute gas, particularly at high temperature and of sufficiently low density. Okay. So what will be actually the mathematical condition or the quantitative idea about this criteria for applying the classical statistics? We can find easily by the concept of de Broglie wavelength. Okay. So I hope you have understand that the basic criteria for the validity of the classical statistics is what? The basic criteria is the distinguishability of particle. Particles should be distinguishable, and particles can be distinguishable only when the wave packets associated with the particle do not overlap with one another, because when the two wave packets will overlap, actually in that condition you cannot distinguish the two particles. The two particles will behave like a single particle. Okay. So this is the basic criteria. Okay. And for this, the de Broglie wavelength associated with the particle must be much smaller than the interparticle separation. And as I have told you that for a best candidate for such a situation, you can take a dilute gas which must be at high temperature, because at high temperature the interatomic separation will be very large and density should be very small. So it is a dilute gas. Okay. Now we will see this fact just in a mathematical way. Okay. And all the facts which I have actually described just now, I have mentioned it here. You can see that a quantitative criteria can be obtained by comparing the de Broglie wavelength with the space available per molecule. If the space available per molecule will be much greater than the de Broglie wavelength, actually then the particles the wave packets will not overlap, and the particle will have individual identity. They will be distinguishable. Okay. So we consider that the extension of the wave packet is of the order of few wavelengths, and if this is much less than the average interparticle separation, the wave packets have little chance to overlap. Okay, and when the wave packet will have little chance of overlapping, or the wave packets do not overlap, only then you can say the particles are distinguishable. Whenever the wave packets will overlap, the distinguishability will vanish, the particle will become indistinguishable. Actually, in that condition you can apply quantum statistics. So don't think that a system of perfect gas or a dilute gas is purely a classical system. This may be treated like a quantum system too at low temperature, because at low temperature there will be a chance that the de Broglie wavelength is comparable to the interatomic separation. The wave packets gets overlapped. In that condition, the particle will become indistinguishable, and then you will have to apply for the same system the quantum statistics. Okay, so never think that a system of perfect gas or a dilute gas is purely a classical system. Never think. It can be a quantum system, but only when the temperature will be small, when the interatomic separation will be small, then that system may be treated like a quantum system. Okay. Now we will actually see this condition by a mathematical way. As you know that if there is a particle having linear momentum p, then the de Broglie wavelength associated with that very particle, lambda, is equal to h over p, where you know that h is Planck's constant. This is the well-known expression for the de Broglie wavelength, that is wavelength of matter wave. Okay. Now, if you consider that our system is in thermal equilibrium at a temperature T, and system is treated like a perfect gas. Okay. So in that condition, for a perfect gas or a dilute gas, you know the intermolecular interaction is negligible. We treat that the molecules of a perfect gas or molecules of a dilute gas is weakly interacting, or in ideal situation we simply say that the molecules of a perfect gas or dilute gas do not interact with one another. Okay, and as you know, potential energy is an energy of interaction. But if the two particles or two molecules of a perfect gas or dilute gas do not interact with one another, there is no intermolecular force existing between these two molecules, then definitely the potential energy U of that system will be equal to 0, because potential energy is energy of interaction. So there is no potential energy in the molecules of a perfect gas. Okay, and as potential energy is 0 for the molecules of a perfect gas, so whenever you talk about the total energy of the molecules of a perfect gas, that means what? That means the kinetic energy, because potential energy is 0, so total energy is simply equal to kinetic energy. And one thing here is also to be noted, you have definitely studied in kinetic theory of gases or perfect gas, that in case of a perfect gas there is only one degree of freedom, which is translational degree of freedom. Okay, one means not only one type, not one. Each molecule of a perfect gas has 3 degrees of freedom, and all those 3 degrees of freedom are translational degree of freedom. So the molecules of a perfect gas has only translational kinetic energy. So whenever you talk about the total energy of a molecule of a perfect gas, that means you are talking about the translational kinetic energy of that molecule. So I have written here, you can see that the average energy of a molecule of a perfect gas, which is denoted by the symbol E, will be equal to what? that will be simply equal to translational kinetic energy of the molecule, because the molecule has no vibrational degree of freedom, no rotational degree of freedom, so its total energy is in the form of translational kinetic energy. And due to the lack of interatomic attraction, this potential energy is zero. And you have definitely studied in kinetic theory of gases that this energy is simply equal to 3 by 2 kT, because you know in general the energy is equal to, in fact, half kT per degree of freedom. This is law of equipartition of energy, and you have studied this fact in your course on thermodynamics, in heat and thermodynamics, that half kT energy is associated with each molecule in thermal equilibrium at temperature T with each degree of freedom. Since the molecule has 3 degrees of freedom, so the total energy of a molecule will be half kT into 3, because with each degree of freedom energy is half kT, so with 3 degree of freedom energy will be half kT times 3, and so this is simply 3 by 2 kT. Okay, so you can say that the energy of a molecule of a perfect gas which is in thermal equilibrium at temperature T is simply equal to 3 by 2 kT. But you know that this E is simply translational kinetic energy, so this E can be written as P square over 2m, because you know that kinetic energy is equal to what? This is half mv square, and this can be written as mv whole square over 2m, but mv is p, so this is simply p square over 2m. So I have written here that E is equal to p square over 2m, and so p will be what? P is square root of 2me, and let us substitute the value of E here. So this will be a square root of 2m times 3 by 2 kT. This 2 and this 2 will cancel out, and so the momentum of the molecule of a perfect gas is simply equal to a square root of 3m kT. Now as you have seen that the Broglie wavelength lambda is equal to h over p. Now, and you have obtained that p is equal to a square root of 3m kT. So substituting this value of p in this expression, you will get that the Broglie wavelength associated with the particle is what? This lambda is h over a square root of 3m kT. Okay. So this is the expression for the wavelength or de Broglie wavelength for the molecule of a perfect gas. Now we will find the size or the space available for a molecule, and for this let us consider that n is the number of molecules and v is the volume of the gas. Okay, so as the volume of n molecules is equal to v, so volume of one molecule will be what? This will be v over n. So the volume available per molecule will be v over n. Okay. Now you know that this geometrical volume is always proportional to some length square. For example, in case of cubical, in case of a cube, you know that volume is equal to simply cube of the length of edge of the cube. Okay, this is its volume. If you consider that this volume is spherical, then this will be equal to 4 pi r cube. Here r has a dimension of length, so definitely volume is always proportional to cube of any length. For simplicity here, we consider that the volume is cubical. And if the volume is cubical and you consider that the length of that cube is equal to L, then the volume V of a molecule will be equal to L cube, will be equal to L cube. And so this L will be what? This L will be equal to V to the power 1 by 3. Okay, but V, you have obtained that this V is equal to capital V over N. So you can say that this L is equal to V over N to the power 1 by 3. This is cube root of V by N. So this is actually the extension of the space of a molecule, and lambda, which you have calculated, that is the wavelength associated with the molecule. Okay. Now, as you know that the two molecules will be not correlated, or you can say that the wave packets of different molecules are exclusively associated with the molecule, they do not get overlapped. How it will happen? When it will happen? Actually, this will happen only when the wavelength associated with the molecule will be much smaller than the extension of the space L of the molecule. So the basic criteria for not overlapping of wave packet for the individual identity of molecule will be what? This will be lambda must be smaller than L, much smaller than L, not smaller but much smaller. Now you can put the value of lambda and L which you have obtained just now in equation 1. You have obtained the value of lambda, and in equation 2 we have obtained the value of L. So we will substitute the value of lambda and L from equation 1 and 2, and what will be our result? So you can see this will be H over root over 3 mkt must be much smaller than cube root of V by N. Okay, and this condition can be written as H over a square root of 3 mkt times N by V to the power 1 by 3 must be much smaller than 1. Okay, actually this is the criteria, or this is the condition or essential condition under which, when will be satisfied, only then you can apply the classical statistics or Maxwell-Boltzmann statistics. Classical statistics is also known as Maxwell-Boltzmann statistics. So I have mentioned it here that the classical statistics can be used when the condition defined in this equation 3 gets satisfied. Okay. So actually this criteria is used only as a guide to decide whether we should use classical statistics or we should use quantum statistics in a gas of identical particles. As I have told you earlier, that never think that in case of a gaseous system we must apply classical statistics. Never think. In case of a gaseous system, we can apply both classical statistics and quantum statistics. If this quantity, which this number H over root over 3 mkt times N by V to the power 1 by 3 is much smaller than 1, then we should apply classical statistics, because in this condition the molecules of the gas will have individual identity. They can be distinguished because their wave packets will not overlap. But let us see, or let us think, if this criteria is not fulfilled, or you can say that if the condition is just reverse, that if H over root over 3 mkt, okay, times n by v to the power 1 by 3, this is much greater than 1. If a condition is like this, then what will happen? Actually, in that condition, the wave packets of the different particles will get overlapped. The wave packets will get overlapped, and the particle will lose its individual identity, and you can't distinguish between the particles or molecules. In that condition, you should apply quantum statistics to deal with that system. System is already that gas, but that depends on the value of the de Broglie wavelength. And as you can see from this expression that this number will depend on the value of temperature T. Here I have told you that temperature T should be very large, because when T will be very large, only then the number in LHS will be very small. But if you consider that our gas is at low temperature, it means T is low, T is small. In that condition, this number in LHS will be very large, and this will be actually much larger than 1. And in that condition, we should apply quantum statistics for the gaseous system. So for the gaseous system, we can apply both classical statistics and quantum statistics. Okay? But it will depend on the fact that our gas is at low temperature or high temperature. At low temperature, if you will take a dilute gas, then you have to apply quantum statistics. But at high temperature, the intermolecular separation increases, okay, and de Broglie wavelength decreases, and in that condition there will be no overlapping of wave packets. Molecules can be distinguished from one another. They will have individual identity, and our classical statistics will be valid. Okay, so I think you have definitely understand that what is the basic criteria for applying the classical statistics. We have also actually discussed that when for the same system we can apply the quantum statistics, but our further lectures will be only on previously only on classical statistics. So after this basic condition of applying classical statistics, we will be very convenient to deal with the problem of classical statistics or Maxwell-Boltzmann statistics. Actually, in the forthcoming lecture, we will see first of all the Maxwell-Boltzmann distribution law, and after that we will see its applications. Okay, so I hope you have understand each and every step which I have actually discussed here. So thank you very much.